Good morning or good afternoon, whatever time you are watching this, and we are focusing on stellar evolution. Remember, stars are not fixed objects out there in the sky. They evolve. They are formed out of gas and dust that exist in the galactic spiral arms. And when gravity is good enough and the density is just right, gravity takes over and pull that gas in. And as this process of slowly contraction takes place, a system, in fact, a star system is formed with as the system evolves itself, circumstellar material rotate around the star, and out of it planets and satellites and comets and all this junk we are learning to exist in our solar system comes to be formed. So, but this is star formation. So stars also they undergo a steady evolution as a main sequence star, and then eventually the fuel, the energy production in their very center part is halted, is gone. So these two chapters on low mass, the evolution of low mass stars and evolution of high mass stars have to do with that. So what happened when the core that provides energy to the star by fusing hydrogen into helium, what happened when this fuel is gone? What happened when the energy production in the core is gone because hydrogen is gone, right? So how do stars get the energy? How do stars get too bright for so long? Well, because they produce energy out of what? Fusing hydrogen into helium. Four atoms of hydrogen are fused into one atom of helium. Okay, good. So what happened, and this happens in the core. So what is the outcome when that energy production process is gone? So this is the main point of these chapters. So let me go briefly through this. By the way, I will tell towards the end what you need to do as far as assignments is concerned. But what is driving evolution? I mean, evolution in a star is slow or fast depending on what. So what is the driving force controlling evolution in a star? That is the stellar mass. So massive stars go very fast through their evolutionary cycle, and low mass stars take longer time in order to go through their evolutionary sequence. Also, what's the definition we are adopting now between low mass stars and high mass stars? So low mass stars are anything that is less than 8 solar mass. Okay, so their steps in evolution will depend on how much or how many kilograms, let's put that way, of mass they do have. And here's your Hertzsprung-Russell diagram of stars evolving in the so-called pre-main sequence phase, the phase that leads to stellar formation. See the arrow pointing from this region all the way to main sequence. So stars are contracting here, and as they do, they become less luminous, they get a little bit hotter, and then eventually they hit the main sequence. And then there they will spend most of their lifetime. And as a main sequence stars, they will be fusing hydrogen into helium in their very core for most of their lifetime. Okay, but eventually, what's going to happen? This is when the star start out its life. 25% per mass of helium, 75% or so of hydrogen, all through the star, because that is the composition of our universe if you think in large scale. But in the core, especially in the sun today, what this graph shows is in the very center core of our sun, 60%, not 25%, but 60% of the central core is helium. Why helium? Because hydrogen during these 4 billion years of sun's evolution has been converted in there into helium, and eventually in another 4 or 5 billion years in the future, the core is going to be entirely helium. And when this happens, fusion is gone in the core, and then stars will undergo changes. In the case of the sun, this implies that now the core is inert. There is no fusion reaction there anymore. With a temperature of 20-30 million kelvins, that is not sufficient to ignite fusion or helium fusion right away. And the pressure, the weight of the stars on the core of the sun on the core is not high enough to stimulate, to ignite further fusion reactions, the helium fusion reaction into carbon, oxygen, and other heavier atoms. So what happened in this stage, and that's what you should be reading, is that the core slowly contracts and the shell in which fusion reactions takes place, a shell surrounding the core, a shell surrounding the core. Fusion reactions takes place where hydrogen is fused into helium. Now you have a burst of energy production, not in the core but in the shell, and that is enough to expand the outer layers of the star. So the star, funny thing happened. It's counterintuitive. For once, the core contracts and heats up, and and these fusion reactions, this that goes on in the shell, is sufficient to expand the star, expand the outer layers. And when this happens, the separation between molecules, atoms in the stellar atmosphere or the outer layers increases. So less collision, the star gets cooler. And as we learned previously, cooler gas in astronomy means redder gas, redder color gas. So the star becomes bigger because it expands, but cooler or redder. So the star is called a red giant. Red giant. Okay. So two things happen: core contraction and star expansion. So this is a question I would like you to answer, and that is part of your assignment. Okay. So what will happen with the sun when it leaves the main sequence? What is going to happen? So helium, to be ignited in the sun, it goes through a flash process, triple alpha process, in which the core that is completely helium, when it reaches 100 million kelvins, entirely ignites in a physical process called helium flash, and then fusion reactions now restarted in the core. Now helium is fused into carbon. Okay, and when these fusion reactions is again operating in the core, the star becomes what's called horizontal branch star. Horizontal branch star because it's kind of the luminosity doesn't change much. The star gets a little bit hotter because fusion reactions is again taking place in the core, helium primarily into carbon and oxygen. But as it happened before with hydrogen being exhausted in the core, helium eventually will be exhausted as well, because helium in the horizontal branch is being converted into carbon. So eventually the helium is all gone. And when that happens, the second stage in which the core start to contract, carbon core started slowly contracting, the star outer layer expands because now you have two shells with fusion reactions going on. One is hydrogen, the other is helium, and the star produces much more energy than before. The star expands and becomes what is a asymptotic giant branch star, AGB star. Okay, and the star grows in size, becomes a kind of a red supergiant, or AGB is a big one. So the radius can go up to more than 100 times the solar radius. I mean, kiss goodbye to Mercury, kiss goodbye to Venus. At least Earth is going to be all boiled down. I mean, there will be no water, no atmosphere, no nothing. Life as we know here is gone. So invest, please put your tax money in space exploration, because we have 4 billion years to get out of the system and look for another star system, since the sun will become a red giant or AGB, and that's it. Kiss goodbye to your life. But we have 4 billion years to go, anyways. Um, and then eventually, since for a low mass star there is not enough pressure in the core to ignite carbon and oxygen fusion reactions, and then that's it. So eventually the shells, the energy production in the shell surrounding the core grows to the point that the outer layers of the stars are expelled out, and this expanding stellar gas, produces one of the most beautiful phenomena in the sky called planetary nebula. Planetary nebula has nothing to do with planets, but is the result of expanding gas coming out of the center star. And the core, this very compact and hot core, is called white dwarf. White dwarf. So what is the end of evolution of a low mass star? Well, low mass star, once it leaves the main sequence, becomes a red giant, a horizontal branch star, an AGB, planetary nebula, and then a white dwarf with an expanding shell, and that system is called planetary nebula. And eventually the gas is all transferred to the interstellar median, and it's left with a white dwarf. And that's the second question of your assignment that you should answer right below this video. Binary begins with a 2 solar mass and a 1 solar mass star. Which of the following stages is not possible later on? Choose A, B, C, or D. Choose well. And now it's a mass of a white dwarf can't be larger than 1.4 solar mass. It's called the Chandrasekhar limit. Chandrasekhar was an Indian astronomer who calculated that, and he got a Nobel Prize for that. And because if the mass goes above 1.4 solar mass, the star explodes. The entire energy, 1.4, is converted into luminous energy. And this phenomenon, this explosion, supernova, is called supernova type 1. Supernova type 1. Okay. Now there is a phenomenon called nova. It's not the show, the PBS show Nova. Nova means new in Latin, and astronomers thought when a sudden brightness of a star in the sky indicated that stars are being born, so they call new star. New star comes when a flash happens. This is not true. I mean, in fact, nova are dying stars. Poor guys. Dying stars. How that happen? Well, we have a binary system, let's say a compact object like a white dwarf being surrounded by a star that is a main sequence. Eventually this main sequence star expands, and then material falls on the white dwarf. What's happening? Well, first the hydrogen, because most of the gas is hydrogen, gets kind of a crummy and compact around this carbon core, and eventually that goes on a flash, and then you have this sudden increasing brightness, several order of magnitudes above the level of the original star, and as a result we see this nova going on, this flash going on. But if this transfer of material keep on going, eventually this whole core is ignited and becomes a supernova if it goes above 1.4 solar masses and breaks the Chandrasekhar limit. Okay, and that's a supernova type 1. Okay, look at the luminosity. Remember, luminosity is energy. 10 billion suns. So take the energy the sun produces now, multiply that by 10 billion. 10 billion. That is the energy liberty. That's why supernova type 1, we are going to see later, are very important to establish distances to very far away objects, because we can see them very far. If you have a galaxy or a quasar that is billions of light years away, and one single supernova type 1 flashes out in the system, we can detect, we can see that, and remember the inverse square law we studied before? If you observe the magnitude, the brightness of that system, and you know the luminosity of it, because the luminosity of a type 1 supernova is known. It's 1.4 solar mass converted into energy. So you know the luminosity, you measure the brightness, kaboom! By inverse square law, you have the distance to where that happened. That's why astronomers were able to find not only the expanding universe, but the accelerated universe. Okay, here's the last question in this assignment. Which of the following is the correct order for the stages of evolution of the Sun? So after the Sun leaves the main sequence, it's going to be a main sequence and then goes through white dwarf and then through planetary nebula or red giant or not. And which one is the good one? Let me show you before I finish this some animation I saw. No, not this one. Sorry. I think it's this one. Yeah, there you go. In this animation, the site is northwesternsierra.edu, and it shows the animation of, there you go, Center for Interdisciplinary Exploration and Research in Astrophysics, and it shows the evolutionary sequence of 1 solar mass star, 10 solar mass star, 20 solar mass star, and a binary system. It's cool. Let me show you that quickly. By the way, I can't read well here, but these numbers are, I think, time. And can you see these circles here? These circles are supposed to be fixed distance to the center star, and if these circles approach the star, it means the star is expanding. Okay, so let's follow the evolutionary sequence of 1 solar mass star. So the star rotates. See, the circle is still there, right? It's kind of moving a little bit slowly. The star seems to be, see, now the circle is going in. Follow with my cursor, which means the star is expanding. Okay, so it's a small expansion because hydrogen is being fused in helium in the core, and eventually this expansion will be faster because the star is becoming a red giant. But most of its lifetime is going to be in the main sequence. Now it's going fast. Boo! And you got your red giant. And then the star is going to go through the horizontal giant branch and then the AGB phase. It's really expanding. It keeps seeing the circles just coming in, right? And kaboom, that's probably the horizontal giant branch, and then it's going to go to an AGB. And then eventually a planetary nebula with a white dwarf in the center. Okay, we didn't see the planetary nebula in there. 10 solar mass star. So 10 solar mass is more, so it's not a low mass star, right? So let's see what's going to happen. So the star, a 10 solar mass, is not a kind of a yellow star like the Sun. It's kind of bluer because it's hotter, it's more massive. But again, most of the lifetime is going to it will be spent in the main sequence. But you see the circles are approaching or narrowing in, which means the star is slowly expanding. Now it's really close and another circle is approaching in here, and then it goes quick, and then go through process by which in the core hydrogen can be fused into hydrogen can be fused into carbon automatically. It doesn't go through the flash sequence, and then carbon, oxygen, and neon. You have all these different heavier atoms up to when the core is an iron core. The star explodes, supernova type 2, and the core is a neutron star. You see this pulsar phenomenon going on. So let's go to an even more massive star. So a more massive star, what's the difference? Well, the difference is it goes also through these different cycles in which different atoms fuse in the core, and they start kind of going a zigzag in as a supergiant, a blue and a red, or a blue and a yellow, and keep going on up to an explosion takes place, a supernova type 2 takes place. But the core is not going to be a neutron star, it's going to be a black hole. Supernova type 2 with a black hole in the core. And of course, black hole, we won't see anything in there. Just keep on going. And expansion, supergiant. And another series of atoms will burn in the core. And explosion, black hole. With a supernova remnant kind of staying around. And the last one, what is this? This is a compact system. You have a white dwarf and a star that is also a main sequence. So it's a binary system, right? A compact object and an expanding now main sequence. Now this guy is going through evolutionary sequence, and if they are close by, mass transfer occur to the primary, which is a compact object. You have this bipolar flow that comes out as a result of conservation of angular momentum. A bipolar flow is a very common issue in young systems and evolved systems like that one. And mass transfer, keep going on. If this compact object is a white dwarf, if the mass goes more than 1.4, it's going to explode in a supernova type 1. But it could be that this secondary here evolves, right, as a white dwarf or something else. And now you have a binary system comprised of a white dwarf and a neutron star. So in fact that would be the neutron star because it evolved prior to the white dwarf. Okay. Anyway, so cool. Thank you. Answer the question. There are 3 questions for you to answer, and have a nice one.